we'd like to consider the idea of taking derivatives of inverse functions that can allow us to derive some other differentiation formulas. But before we do that, let's look at just kind of review a little bit about inverse functions, some of the main properties that we might need. So this is saying, suppose you have a strictly increasing or decreasing function. You might recall that means the function's 1 to 1, which means it does have an inverse. Then this is how we define the inverse. And I prefer this notation better. I prefer when I plug into f, it gives me an output of b. Then what the inverse function does is it takes that value b back to where it came from. So it's the function that's undoing whatever f did to give me b. F inverse is taking that number and returning it back to where it came from. So that's the idea of an inverse. And this statement is equivalent. If you look at what that's saying, it says, let's start with, let's do this one. When I say that this equals x, what I'm saying is I'm plugging a number in to f, and it's giving me an output of something. I call it b here, but here I'm calling it f of x. It's giving me an output of b, and then what f inverse is doing is it's going to take that number b back to where it came from. Well, that's what this is saying. I'm taking whatever this was, and it's going back to what I originally started with. It's taking the original number I plugged in, which was x, and when I run it through f and f inverse, it's going to spit it back out as x. So this is a compact way of saying exactly the same thing, and then reversing it here is both of them work. So that's the idea of what the inverse does. So here's an example. I've got f of x equal x cubed plus 8. It turns out there's a way to show that the inverse function, the way to derive that the inverse function is the cube root of x minus 8. So for example, if I take the number 2 and plug it into f, it gives me an output of 16. Equivalently, that's what the double arrow means. I didn't say that up here, but the double arrow means equivalently, or if and only if. If I take the inverse function and plug in 16, that's going to go here. 16 minus 8 is 8. Cube root of 8 is going to take me back to 2. So I can show that for every individual value. That's what this original statement's saying. But I can also show it all at once by just taking f of f inverse of x. So in this case, whatever I plug into f, I'm going to cube it. So I'm going to be cubing f inverse, and then I'm going to add 8 to it. Well, f inverse, the definition is it's the cube root of x minus 8. That's what I'm going to be cubing and adding 8 to. But cubing the cube root gets rid of the cube root, so now I just got x minus 8 plus 8, and you can see the 8's are going to cancel, and it returns me back to x. So whatever x I plug in to f inverse, this whole process will return it back to the x it started at. And likewise, you could turn it around and do f inverse of f if you like. So that's another useful property. And another one that we probably won't use much here is the fact that when I say that f of a equals b, that tells me the graph contains the point x equal a, y equal b. That's the graph of f. But then the graph of f inverse, when I say that f inverse of b equals a, that tells me that the graph of f inverse contains the point b, a. So they're reversed. And that has the property that if I draw the line y equal x, the way I reverse these x's and y's is I flip the graph across that line. So if I have a graph it's supposed to be strictly increasing, so kind of messed up there. That's close enough. I can draw its inverse by just drawing the mirror image on the other side of this line y equal x, so it looks something like that. So if this is f, this would be the graph of f inverse. Well, one of the important inverse functions for us is the fact that if I have f of x equal e to the x, then its inverse function is, we just make up a name, natural log of x. I can draw its graph. Here's the graph of e to the x. Remember, it's an exponential growth problem. And so f inverse, which is natural log, would have this graph, which we've already done. We've seen it. Because f of 0 equals 1, that is, e to the 0 equals 1, f inverse of 1 equals 0. We can see that. And that happens for every point on the exponential function and the inverse function. The exponential function has a horizontal asymptote of y equals 0. So when we flip things around across this line, natural log has a vertical asymptote at x equals 0. We can evaluate things nicely for natural log as long as they're powers of e. So if I want to evaluate natural log of e squared, that's an easy problem because it's natural log of e. This is the f inverse of f, and all I get is the 2. It's not so easy to evaluate it at 2 because I don't know what it takes for e to give me 2, because e itself is 2.1782817, so I don't know what power to raise it to end up being 2. But nice powers of e give me nice outputs from natural log. So, as long as I'm doing natural log of e to some value, I can always do that, or the other way around, e to natural log of some value. They always cancel out. So that's a very brief review of inverse functions. What we want to do is now use them to do some calculus to learn a few more derivatives.